I can call now then Artem on stage for the next presentation about the Velta tea process. There he is. Hello.
Yeah. Hi.
Can you share your slides?
I can share myself. Yeah, I think. Yeah.
Yeah.
1 second.
Coming. Okay. So.
Can you see it?
They're not visible yet for me, but yes, now they are.
Yeah.
Okay. So I think I will leave the floor to you, and me and Nikolai will just switch off our cameras and leave you on stage. Thank you.
So good afternoon or good evening, everyone, depending on where you are joining us from. My name is Artem Yarovinsky, and I represent Velta REPTiS, and today we are going to talk about fundamental shifts in titanium production. For decades, the industry has relied on the same complex, energy-intensive metallurgical routes. Our Velta tea process challenges this tradition by offering a direct chemical pathway from ilmenite to low-carbon titanium alloy powders. My goal today is to show you not just a new powder, but new production architecture, I would say, that bypasses the traditional sponge and ingot bottlenecks, integrates zero-waste logic, and lowers carbon emission. So to do that, today's presentation is structured into the 6 logical blocks. First, we'll briefly discuss the strategic context of the European titanium supply chain, which already Bruno previously shared. Second, we'll look at the current industrial benchmark, the CRO process, combined with AGA to identify exactly where it hits the environmental and economic limits. Third, we will dive into the core of the Velta tea process, focusing on our hydrometallurgical platform with alloying at oxide stages. Then we'll have a look at circular economy of the technology and the waste transformation, which leads to co-products manufacturing, and discuss morphology and how our platform adapts to downstream technologies like metal injection molding and additive manufacturing. And finally, we will look at the hard numbers, breaking down the specific energy consumption and life cycle assessment impacts of our process. So let's begin with the strategic context. Yes. So titanium is a critical raw material due to a combination of characteristics you might know: outstanding specific strengths, excellent corrosion resistance, stability at elevated temperature, and absolute biocompatibility. And this is why titanium alloys form the foundation of critical technologies like in aerospace, defense, medical sectors, additive manufacturing. However, if we look at the current situation in the European Union, we see, like I also said that Bruno shared previously, a deep critical dependence on the import of titanium intermediates. This vulnerability is not just about the access to primary ore. It affects the intermediate stages of value creation, like sponge production, ingot melting, and high-quality titanium powders. This exact vulnerability has driven a shift in the industrial paradigm, I would say so. In the past, the central technological question was simply, can we produce produce titanium powder? And today the requirement is much stricter. Can we produce high-quality titanium powder with lower carbon footprint? And can we deploy the production within the resilient supply chain? So the REPTiS project itself aimed at solving exactly this challenge. It links rich Ukrainian ilmenite resources with a new metallurgical route and subsequent European powder validation in the form of parts. Okay. The REPTiS project is built on a full cycle principle. Our value chain creation map consists of 4 fundamental segments. You can see it here in the boxes. We start with the raw material section, which includes the extraction and beneficiation of ilmenite bearing sands. The second block is chemical conversion, where the mineral feedstock is purified and converted into intermediate titanium dioxide. The third block is powder and components. Here, the purified chemical matrix is transformed directly into metallic alloy powders, which are then sent to downstream production for parts. And the fourth block, and I want to highlight it, is byproduct valorization. In our approach, this is one of the core elements. So our goal was to design the technology so that process residues and chemical side streams are turned into useful commercial products. Let's start, the starting point of process is ilmenite. In traditional industry, ilmenite is most often viewed as a feedstock for pigment production or as a raw material that requires complex preliminary upgrading. Within the Velta process, we change the perspective. For us, ilmenite is a complete chemical platform for the direct production of titanium alloys. Because our method is direct chemical process, the quality of the initial concentrate has a direct impact on all subsequent stages. The titanium dioxide content, the valence state of the iron, the residual trace elements, all of them strictly determine the mass balance, the purity profile, and the overall economics of the process. And before going further in detailing our technology, let's recall the current global industrial standard, the combination of the Kroll process and the gas atomization, known as, in the specific here, EIGA method. This is proven commercially successful technology capable of producing excellent spherical powder. It is true. The problem is not this method doesn't work. The problem lies elsewhere. The colossal energy consumption and massive carbon footprint accumulates through a long chain of high temperature transformation, long before the first particle of powder is formed. So let's look at this classic flow sheet. We start with high temperature chlorination to produce titanium tetrachloride. This is followed by reduction with the magnesium to produce titanium sponge. But titanium sponge is a porous pure metal. It contains no alloying element at that stage. And to obtain wide-known Ti6-4 alloy, the sponge must be mixed with alloying additives and subjected to repeated vacuum arc remelting. The resulting massive ingot is then forged and machined in the form of electrode. Only after that, the electrode is melted by induction and atomized in EIGA unit. So every step here is in this rigid chain means new costs in energy, in time, and technological losses throughout the way. The key bottlenecks is the sequential nature for the chain itself. So first, chlorination stage requires working with free chlorine and high temperatures and generates massive chloride wastes. Secondly, the isolation of the sponge stage. So industry creates metal in one form and then performs a multitude of energy-intensive actions to convert it to another form suitable for atomization. Third here, repeated ingot remelting. So with this vacuum arc remelting, it means huge electricity costs and long production cycle just to eliminate elemental segregation. Fourth, atomization yield limits. So with the EIGA, you create a wide spectrum of particle sizes. Everything larger or smaller than the required fraction has to be reprocessed back or sold at a discount price. This led to a question, is this long sponge ingot electrode route really necessary just to obtain an alloyed titanium powder? Now we are getting to the Velta process, and this slide presents the logic of the process in its simplified end-to-end form. So instead of converting the feedstock into titanium tetrachloride, we apply hydrofluoric acid hydrometallurgy to transform the raw material, which is here ilmenite, into a pure oxide platform, high purity titanium dioxide, or as we call it internally, isoinrutile. And here is our main qualitative difference. We aim the design of the future alloys at the oxide stage, prior the start of the metallization stages. alloying the components like aluminium and vanadium are introduced directly into the purified oxide matrix, and the chemical composition and homogeneity of the future alloy are formed chemically in this precursor. After the homogeneous oxide precursor is obtained, it is sent to a two-stage of metallothermic reduction, magnesium and calcium, to completely remove oxygen and convert the precursor into a low-oxygen titanium alloy powder. The output powder has a highly developed irregular shape, ready for direct use in several downstream technologies, or it can be converted into spherical morphology. This direct pass from mineral to alloy completely bypassing the intermediate stages of sponge and ingot melting. Let's break down the first basic node, so hydrometallurgical production of the oxide. So the process begins with hydrofluoric acid decomposition at moderate temperature around 120 degrees Celsius. This results in titanium oxychloride solution alongside chloride of iron. The stage is built on selective elemental separation, titanium transfer into oxychloride solution, while iron is directed into separation streams. This insoluble sludge is filtered out and sent to produce Velta, which is our titanium-rich additive for blast furnaces. The purified titanium oxychloride on the opposite way solution undergoes controlled hydrolysis, washing, and then calcination we have. So the output high purity titanium dioxide, and again, this is not a final pigment. It serves an ultra pure matrix for subsequent alloying. A vital energy engineering solution here is a fully closed loop for hydrofluoric acid. All acid vapors generated during hydrolysis are efficiently captured, condensed, and returned back to the primary or decomposition stage, minimizing fresh acid consumption. So this closed loop technological platform is designed on near zero, like my colleague Andrei liked to say, near zero liquid discharge principles. So the process ensures that processed water does not become the effluent itself. All circulating filtrates and wash waters undergo multi-stage purification and are returned to the system, eliminating the risk of hydrosphere, if I could name it like that, contamination. More concentrated solution streams directed to nodes for the selective extraction of co-products or to final salt crystallization stage. So by purifying water for reuse, we concentrate the valuable chemical elements and turn them into marketable products. From the perspective of life cycle assessment, this provides a big advantage because byproduct commercial streams take significant share of the overall environmental burden of the enterprise through like systemic allocation. As a result, the specific environmental and carbon footprint for main product titanium powder is highly reduced. I would try to be brief on this slide. So this slide outlines the commercial co-products we obtain with a single technological cycle. The first large group is iron oxide pigments, black, red, and yellow, synthesized from iron chloride solutions, which I mentioned previously. These are high in demand for coatings, plastics, construction materials. The second group is mineral fertilizer. Specifically here is ammonium sulfate, converting nitrogen and sulfate streams into this agricultural product. We also produce Velta BF for ferrous metallurgy sector and PCC, which is precipitated calcium carbonate, the high quality filler. We extract inorganic flame retardants such as magnesium hydroxide, aluminum hydroxide, sodium silicate. Additionally, sulfuric acid, the metallic calcium function is integrated reagent nodes to cover internal needs, and every sulfur can be sold on the market basis. Also, like you might previously heard and should heard from me, so in traditional chrome metallurgy, alloying occurs after the pure metal is obtained. In our case, we perform alloying much earlier and at the oxide precursor stage. So I will repeat once again: the titanium dioxide serves as a base. To obtain Ti6-4, which is popular, we introduce precisely dosed chemical compounds of aluminium and vanadium to form homogeneous complex oxide precursor before the reduction steps begins. Next, it goes to two-step metal thermic treatment. First one is the magnesiothermic reduction, and the second stage is deep calcium deoxidation that pulls the residual oxygen out of the titanium lattice, bring it down to like strict target specification. And about the specification, we will talk further here. So for titanium alloys, interstitial elements, especially oxygen, are critical. Oxygen strongly increases the strength, but an excess leads to drop in ductility. And here are the actual analysis results of irregular T6-4 powder batch produced using our technology. The oxygen content here you could see varies from 0.1 to 0.12 in weight percent, which you see that it's below the industry limits. And here are some photos of the morphology of such powder. The Velta T process itself is a flexible and configurable powder platform. So different downstream technology have different requirements, like for metal injection molding and present sintering. Fine irregular core-like powders are highly effective due to their green strengths and packing density. But for additive technologies like laser bed fusion, where perfect flowability is critical, the powder requires to be processed through the plasma spheroidization or other techniques. We also are actively developing inside the REPTiS framework the Velta LTS, low temperature spheroidization, to obtain spherical geometry with significantly lower energy costs. So morphology, long story short, morphology is controllable process parameter. The powder can be in the shape that fits the customer technological requirements. I will talk briefly here. Powder is not the ultimate goal in the REPTiS project in whole. The finished parts is, so if, just an example I put here is metal injection molding for proving ground of irregular powders. The powder is mixed with thermoplastic binder to create a feedstock. The irregular shape ensures an excellent mechanical bond with the polymer. This feedstock is injected, form green part, then goes through debinding where polymer is removed with the final high temperature sintering to consolidate the part. And for additive manufacturing, like I said, the chain relies on the free flow of spherical powders, particles, for which it could be optimized through different spheroidization or atomization techniques. Okay, let's move to the quantitative estimates. This slide shows the specific energy consumption per kilogram of finished Ti6-4 powder. The traditional crawl process with AGA atomization requires 109 kilowatt hours per kilo of powder. Everything here is per kilo of powder. In contrast, the direct chemical processing for producing our irregular powder requires only 39.4 approximately kilowatt hours. And if we add to that plasma spheroidization for additive manufacturing, it will end up approximately 73 kilowatt hours. And for our low temperature spherical route, we estimate within the project to get around approximately 40 kilowatt hours per kilogram. So this represents the reduction in primary energy intensity to up to 64% compared to the global standard. And for the global standard, like I said, Kroll and Dega, we are taking. This is driven by the route itself, by bypassing the energy-intensive sponge reduction and repeating remelting and induction melting in the atomizer itself for the powder production. And here's the next slide is for carbon footprint metrics. We used the average intensity factor for electricity, 0.4. You can see it, kilogram of CO2 equivalent. So the traditional Kroll EGA chain generates approximately 47 tons of CO2 per ton of powder. Our direct process for irregular powder generates about 8.2, and this is 82% reduction in the carbon footprint. Because our zero waste platform concurrently produces large volumes of commercial chemicals and mineral products, a significant part of overall carbon burden is transferred to these combined streams. And I already get to the summary. So to conclude, I want to establish, like it's written here, 5 key takeaways. So first, Ukrainian Ilmenite is a highly efficient chemical platform for the direct synthesis of advanced titanium alloys, not just a pigment feedstock. Second, by bypassing the conventional sponge ingot electrode sequence, the Velta T process eliminates excess cost in energy, time, and waste. Third, alloying at the oxide stage guarantees chemical homogeneity prior to the metallization, and after also actually force the low carbon Ti6-4 powder produced now continues to undergo the REPTiS project downstream validation. Right now we have a couple more years to go with the project. And last but not least, deep valorization of co-products is fully integrated into the scheme, changing the life cycle assessment economics. That's all from my side. Thank you for your attention. If any questions, I'm happy to ask. And how I should stop sharing the screen.
Thank you, Artem. As before, I would like to open the session for discussion if there are any questions. I don't know if anyone wants to ask anything from Artem. As I said, we are progressing with the validation, so there will be results soon with the properties of the powders.
Yeah.
In the meantime, if you have questions on the process, here we are. I don't see anything in the chat.
It either everything is understood or neither.
Maybe there is a question. I see someone typing or not. You can open your microphone if you want and just ask. It's probably simpler. Maybe it was a false positive. Maybe we can add something, Artem, if you want to say something about the fact that we are not only working on titanium in the project, but we've also, as I mentioned before in my presentation, you're also thinking about the kaolin, for instance. There are also these other critical raw materials or raw materials in general that can be...
Yeah, it goes beyond the Velta T process, yeah, but with the mining side, within the project, we discovered that we have a high concentration of other critical and actually rare earth materials in the ilmenite. and also found valuable materials like kaolin, which is used in ceramics and construction industries within the deposits. So we are now estimating the valorization, putting on the balance. So we do everything to see how it would be not only in the scientific way, but in the industrial, commercial way put in the action.
Oh, there's a question from Mikhail Shvisky. What is the approximate cost for 1 kilogram of Velta 84 powder?
Oh, it's a great question. It's a great question, and I will try to answer. So I would answer like this. For now, we have the pilot scale line, which is located in Ukraine, in Dnipro city. And when we are talking about the industrial way, when we are producing like hundreds or thousands, even tons of titanium powder, it will cost 2-3 times cheaper than the powder on the market in terms of production costs. And in terms of marketable costs, like for price that you can buy, it will depend on when we will have the industrial scale facility. If the powder at that day will be 150 kilos on the market, we'll make it cheaper, but I don't know the situation in a couple of years, what it will be.
Okay, you managed to reply. Anyone else? Yeah, Celso, Roberto. It's also possible to produce cobalt, chromium, molybdenum powder alloys with your technology?
Cobalt, chrome, molybdenum technology. Is Andrei Gonchar here on the call? Yeah, I see him. Maybe he can jump on and answer this, because the main scientist of the technology is Andrei, who is head of our R&D, and he is on the call. Maybe he will address. Andrei, are you here? You can switch on the mic, I suppose.
I can try to reach him if he's there. Yeah, let's see if I can start his microphone.
Yeah, you can try, but basically I will try to answer myself. So with this technology, we're able to work with the titanium-related group elements like zirconium, hafnium, other materials. For cobalt, chrome, and molybdenum, I'm not sure they're, and I'm pretty sure they're not from this group. So I would say if they do not need metallothermic reduction from oxide stage to get rid of the oxygen, then we won't be able to do that.
But it's not needed, let's say.
Yeah.
See, other people are typing, so maybe you can wait a little bit. You can open your microphone, right? It's not...
How the particles are controlled. So we control the particle size distribution of powders on the forming stage before the metallization. So on the stage, when we are preparing the oxide precursors, we already control the particle size distribution. And with a high yield, higher than 97%, if I'm not mistaken. So we will have the same yield after the metallization stage. So the key is controlling the correct feedstock preparation for the metallization.
Right. Any more questions? There were maybe someone else typing, but maybe they changed idea. Okay. If no more questions, then maybe I don't know if also Nikolai can join on stage to thank you. Thank the lecturers for the presentations. There he is. And of course, thank the attendants for being here in our webinar. And we will have more editions of this training series. You will learn about other steps in our project and other topics that we will be touching. Maybe talking about the technologies for characterization of the powders. We will give some details about the results, of course, while talking about the methodologies, and also about the validation with the components, for sure. And so thanks for being here, and stay in touch. Don't forget our workshop in Budapest. If you happen to be in Budapest, we'll be happy to have you also in that event, which will cover the whole supply chain, not just the powder metallurgy side, also the other part of the supply chain that is, well, probably bigger than the powder metallurgy one, and so it could be interesting for everyone. Thanks again. Have a nice rest of the day, and yes, say bye to everyone.
Bye-bye.
Bye. Thank you.
Thank you.
Bye.